Hey guys, so welcome back, and we wanted to start off with a real fun lesson on inclined planes. So just in case you're saying to yourself, man, why do I need to learn about the inclined planes? I got so much better things to do. Well, it could help you get on Wipeout Canada. So here's a little clip from when I was on Wipeout Canada a long time ago, and I didn't do so well on an inclined plane.
Approaching the slippery stairs.
And Professor Latte proves that a body in motion is funniest when it's falling down the stairs.
Is that the slide rule?
No.
So here's another video that is twofold. So one, the train is going up an inclined plane, and we're learning about inclined planes. But secondfold, I know this online learning thing can be hard, and I think we need to follow the same motto as the little engine that could when trying to get through this stuff, because it's gonna be tough.
I think I can. I think I can. I think I can. Now she ran steadily up the track. I think I can. 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 At last she reached the top of the mountain. And then she popped out joyously. I thought I could.
Okay, so now to some real stuff. So we're going to draw a Freebody diagram of the forces acting on the little engine that could on its way up the hill. So we'll start off with some easy ones. So going straight down is going to be our force of gravity, right? And then there's a force bringing it up the hill. So there's going to be a force applied that's up the hill. And then there's probably some friction. I don't know if it's accelerating or not, but there's definitely some friction down the hill. And then the last one is a force normal. And force normal is always exerted by the surface, so it needs to be perpendicular or 90 degrees from the surface. So my force normal is actually going to be at a little bit of an angle there, which is a little bit different than what we've done before. So that's what our free body diagram looks like, and you can see that the force applied looks okay, the force of friction looks okay, the force of normal looks okay. They're all kind of slanted, but they all are 90 degrees to each other. So the only one that's off is our force of gravity here. That one's not 90 degrees. But if we take this and we even it out, right, we can see that, oh, look, this looks totally normal here. It's just that force of gravity that's a little bit off there. So what we need to do is we need to take that force of gravity and we need to break it into these two different components. And if we break it into these two components, which look like y and x, but we don't call them y and x, I'll explain that a little bit later. If we break those up, then this force of friction, that x component, force applied, they all are in the x component, and then the y component here and force normal, then they're all in the y component. So then that's what we need with two-dimensional motion. We can't have things going at an angle. Yeah, so I think I just say the same thing here. I don't know why I repeated the slide, but we need to break it up into this component, and then we'll be all good. So what makes it tricky is we're always given the angle of the incline, but we want to break it into FG into this component and this component. So what does this angle equal in here? Well, we know that this is 90 degrees, and we know that this is 90 degrees. So let's just say that if this is 30, then this has to be 60 here, this angle in here, because this is 90 degrees, and then that would equal all 180, right? And we know that this line makes 90 degrees, so if this is 60 right here, then this is 30 in here, which means that this angle and this angle are the same, right? So this angle is the same as this angle here. But I have a better way of helping you remember that. So instead of breaking that down every single time, what we can do is we want to find these FG lines here. So FG line. All we need to do is find FG sine. Line, sine, line, sine. So the lines refer to the parallel component, and when we show that on our free body diagram, the next question will make more sense. And this is our perpendicular. So instead of calling them y and x, we call them parallel and perpendicular. So FG line, FG sine. And if I want to find FG perpendicular, I use FG cos. And that's not anywhere in your data booklet. You can just remember it. It's line, sine, line, sine, line, sine, and perpendicular is cos. Okay, so we'll try that out in the next question here. A 275 Newton box is sliding down a 35-degree incline. With the force of frictional lines, 96 newtons, determine the magnitude of the box's acceleration. I'm going to switch to my whiteboard view here. Sorry for the glare. I can't do anything about that yet. So let's take a look at this. So we have an incline. Right, all incline plane questions, you always want to start with a free body diagram. 35 degrees, that's where we're going to put that there. And then we have a box on that incline, and we can start drawing on some forces. So the easiest force is straight down. That's our force of gravity. And they gave us a weight. They said it was 275 newtons. So that's the weight of our box. And they also told us that the force of friction is 96 newtons. So the force of friction is going to go opposite the direction that the box moves. And since the box accelerates down the ramp, which means that the force of friction is going to be up the ramp at 96 newtons. So right in the nice glare spot. Okay, I'll try not to write in the glare. Great. Let me just start that again and get that out of the glare spot. Force of gravity is down, and it's 275 newtons. And there we go. Now we can see this. And then my force of friction equals 96 newtons. Okay. And there's a force normal, which is perpendicular from the surface. Not straight up, but perpendicular from the surface. Right? And we don't really know what that is, but we can label it force normal. And the way our diagram looks right now, it looks like there's nothing actually accelerating it down. So that's when we break that force of gravity into the two components. So we have this component here, which to our surface is perpendicular. So we call that FG perpendicular. And then this is our parallel component, right? And this is always going to be 90 degrees right here. Let me fill in the 35 degrees as our angle. Okay, so this force of gravity parallel, it looks like it's down here, but we can move those forces around and we can make it part of our free body diagram. So I'm going to move that here, and this is our force of gravity parallel. And all we care about are the forces along the direction of motion. So when I write my F net equation, I'm going to make down positive because it's accelerating down, up negative. Oh, almost in my glare spot again. So my F net is going to be equal to that force of gravity parallel minus my force of friction. So F net we always can break down into MA. FG line, remember, is equal to FG sine theta. And force of friction we don't have to break down because, well, force of friction is, we know it, it's 96 newtons, so we don't have to break it down. So we just have to move our mass down there. So we know force of gravity, 275. We know our angle, we know our force of friction, we just don't know our mass. But our mass is always easy to find if we have a weight. So to find our mass, we would just go Fg equals mg. Fg divided by g is going to be our mass. So if I go my Fg, 275, divided by 9.81, I end up getting 28.0326 kilograms. So that's going to be my mass that I'm going to use. So now I have everything. So my Fg is 275 sine of 35 degrees. And my force of friction is 96 newtons. Newtons in there. And then my mass is at 28.03261978. Kilograms. Okay, so now we're ready to type that all into our calculator. Sorry, this camera is not the best. I tried to use my iPhone, but then it was a movie and it didn't work last night, so I'm using a document camera, but it's not the greatest. I wish you could see the calculator a little bit better, but it's all I have to work with. So we have 275 newtons sine of 35. And then we're going to subtract 96. And then we're going to divide by 28.03261978. And we end up getting we have 3 sig dig, so 2.20 meters per second squared. And that's the magnitude of our acceleration. Okay. So let's try another one. Let's go back to our PowerPoint view. So this one's about as tricky as they can get. So a large truck with a mass of 2,500 kilograms is accelerating 1.8 meters per second up a steep hill with a 40-degree incline. The coefficient of friction between the road and the tires is 0.8. Find the force applied by the engine to accelerate the truck up the hill. Okay, so a lot of information into there. So I'm going to switch back to my board view. So with this incline plane, I'm going to make it nice and big and not in my glare spot so that everything fits on there. So I'll fill in this 40 degrees. And we have our truck with a mass of 2,500 kilograms there. And now we just need to fill in the forces. So it says, well, let's put in our force of gravity first. So our force of gravity, and we don't know that, 2,500 times 9.81. So we can figure that out. We don't need that yet. And it says that it's accelerating up the hill, so the engine's obviously applying some sort of force to accelerate it up the hill. It also says that there's a coefficient of friction, which means that there's a force of friction. It's going to be smaller than that force applied. And then I have a force normal that's upwards like that, perpendicular to the surface. Okay, so it's really important with every inclined plane question that you break down your force of gravity into a perpendicular component and a parallel component, right? And I'm just going to move that parallel component so it's part of our free body diagram like that. And it's coming from the center of our object. So if you didn't do that, then lots of people would get that force of gravity parallel, and that's part of our free body diagram, or it's part of our F net equation. So up the hill, down the hill, up is positive, down is negative. Now we're ready for our F net equation. So our F net is equal to our force applied minus our force of gravity parallel minus our force of friction. Those are both minus because they're going down. When we set that down, it's negative. So we are trying to find this force applied. So I'm just going to rearrange it like this. I'm going to add a force of gravity parallel, add a force of friction, add a force of gravity parallel, add a force of friction to both sides. So then we end up getting F net plus my force of gravity parallel plus my force of friction is equal to my force applied. Now I'm going to start breaking stuff down because I don't need to rearrange anymore. So F net we can break down into MA. FG we can break down into MG. And lines we can break down into sine. Right? And force of friction we don't have this time. They just gave us a coefficient, so we have to break it down into mu Fn. So we have our mass, we have our acceleration, we have our mass, we have gravity, we have our angle, we have our coefficient of friction. The only thing we don't have is this force normal. And if we take a look at our free body diagram, normally force of gravity is equal to force normal, but not on an inclined plane, right? When we look at what cancels out this force normal is going at an angle here, and force of gravity is going straight down. It's actually this force of gravity perpendicular that is equal to our force normal. And I told you that our force of gravity perpendicular, because line is sine, so the other one is cos. So FG we can break down into mg, and then this one we can break down into cos theta. And that's going to equal our force normal. Right? So I can add that to my formula if I wanted. So MA plus MG sine theta plus mu, and then our force normal is equal to mg cos theta. And you can do this in chunks or you can do it all in one, but it's up to you, whatever you want to do. So now we're ready to solve this question. So my mass of my truck is 2,500 kilograms. My acceleration is 1.8 meters per second squared. My mass is 2,500 kilograms. My G is 9.81. And then sine of our angle, which is 40 degrees. And then we're going to add on our coefficient of friction, which is 0.8. And then 2,500 kilograms. And then our G, which is 9.81. And then our last one, which is cos of 40 degrees. I don't know if I'm off the screen at that point, but yeah. So we can plug this all into our calculator, making sure we use some brackets nicely here. So 2,500 times 1.8 plus 2,500 times 9.81 times sine of 40 plus 0.8 times 2,500 times 9.81 times cos of 40, and we get our force applied is 3.2 sig digs with the angle, 3.5 times 10 to the 4 newtons as our final answer. So that one's a doozy. That's as hard as it could possibly get, but yeah, you will see many like that. There is one in the homework that's like that. Okay, we got one more question that we're going to do, and then we're all done. So let's switch back to our PowerPoint. So this last one's a little bit easier. It says that a 200 kilogram slippery seal is sliding down a 30-degree inclined plane at a constant velocity. Ooh, that's an important piece of information that is going down at a constant velocity. Determine the coefficient of friction between the ramp and the seal's slippery body. So again, we're going to draw a free body diagram for this. So draw my inclined plane. It doesn't matter which way you draw the inclined plane. So we have 30 degrees. We have our seal. Our seal is 200 kilograms right here. And we have a force of gravity down. And we don't know that force of gravity yet. And that's all the information that the question tells us. Right? So we can break down this force of gravity into a perpendicular component and a parallel component, and I'll add that parallel component to my free body diagram. I'll move it up there, and it says it moves down at a constant velocity, and we want to find a coefficient of friction. So because it moves at a constant velocity, what we know is we know our force of gravity parallel is equal to our force of friction. Right? And then we also have force normal that's perpendicular to the surface, and as with all inclined planes, we know that, I'll do that some other place, our force normal is equal to our force of gravity perpendicular. Right? So I'm going to break this formula down. So Fg I can break down into mg, lines I can break down into sine, force of friction equals mu Fn, and that's what we're trying to find to determine the coefficient of friction. And I also know that my force normal is equal to this guy, right? So Fg always breaks down into mg, and this perpendicular signal breaks down into cos, like that. So if I move my force normal underneath, like that, and I break down, oops, running out of room. Maybe I'll just move it over here. So mg sine theta, and my force normal is equal to mg cos theta, and that's going to equal my coefficient of friction. And look at that. Mass and gravity both cancel out, so it just ends up being sine of 30 degrees divided by cos of 30 degrees, and I get my answer. So when I do that, sine 30 divided by cos of 30, I end up getting 0.5758 to 2 sig digs, and that's my final answer. So that's all the questions. You can see that there's some homework questions, and you'll find those in your workbook like we did before. That standard of excellence question is like that second example that we did. That was pretty tough. So yeah, give that a go and see how things go. So good luck with that, and yeah, enjoy.